Hey kids, hope you're having a good Sunday. I got a request for instructions on how to set up that calculator emulator that I was using in the previous videos. So I'm going to start with that. Then I'm going to talk a little bit about exponential growth and decay, which is just the application of the exponential function that we learned last week. And then I'll do a couple of homework problems to be sure you're headed in the right direction. So here I am at Google, and I'm just going to type in TI-84 emulator. It's one of the first suggestions that comes up, and what you'll get here is this Wabbit Studio Z80 software tools. So let's click on that, and then this nice big purple button here that says download. And it gives me this guy right here, so let's save file and open her up. Now you'll get this dialog box here, and what you want to select is create a ROM image using open source software. Next, there are all these options here. I've got the TI-84 plus C SE at home, which is great, but what you've got in the classroom and what you'll have on the STAR test is just a TI-84 plus. Nothing else, nothing fancy. So pick TI-84 plus. Click next. It should be set up correctly. Download OS files from TI website. OS 2.55 is what we want. And finish. And it's going to pull up a dialog box and ask you to save this ROM file that you're downloading. So let's just call it TI-84 emulator, and be sure you pick a good location to save it. I'm going to put mine on the desktop so I don't have to go looking for it later. And then save, and it's going to load the OS, and then it'll pull up this tiny little window right here. You can big screen it. Now it feels a little funny, so what you want to do is go to View, Enable Skin. There you go. So View, Enable Skin, and then you get the calculator and you can size it however you want. It works just the same as the calculator we have in class. There we go. You probably want to check with your parents before you do that. I also noticed on the website that if you have an Android device, a phone or tablet, that there is an Android app that contains this emulator. Alrighty, so here is a generic look at exponential growth. This is a times b to the x, where a is bigger than 0 and b is bigger than 1. Probably between 1 and 2, but could easily be larger depending on the situation. A is our initial value, our y-intercept. That is, where do we start? Where does the growth start? And then b is the rate of growth, which is usually 1 plus some percentage. And this exponential growth function is always going to look a bit like this. It gets super flat as it goes to the left, getting infinitely close to 0. And it heads off towards infinity at one rate or another as it heads to the right. And then usually this point right here is where we start looking, the initial value. So even though we've got this part to the left, when we're talking about exponential growth, we usually only go from x equals 0 on. And if you look at number 20 from your homework on page 776, you'll see a good example of this. It's a physics problem about a ball rolling down a hill, and the function of its speed is y equals 1.3 times 1.41 to the x power. So here you can see the initial value is 1.3, and the rate of change, or the rate of growth rather, not the slope. We aren't talking about slope here, we're talking about rate of growth, which is 1.41. Or in other words, 41% above constant. And the question asks, how fast will the ball be going after 15 minutes? So we let x be 15, and we trust our calculator to tell us the right answer, because nobody wants to raise 1.41 to the 15th power. So we could say 1.3 times 1.41 raised to the 15th power. So 225 inches per second. And we could also have a look at the function in y equals 1.3 times 1.41 raised to the x, and have a look at the graph and notice how it has this exponential growth shape. Starts flat, comes in and touches our initial value, and then begins to take off at an exponential rate. Zoom in here and you can see that the y-intercept is indeed a little bit above 1 at 1.3. And of course the table tells us the same thing, as well as our value of y, the speed, when x is 15 minutes. Alright, and then now I've changed the template to represent exponential decay. Here a is still greater than 0, but now b is going to be somewhere between 0 and 1, because remember that reflects the graph across the y-axis, and now we're decreasing as we move from left to right instead of increasing. And this is usually modeled with 1 minus the percent of decay. So if you look at the sports problem, number 18, we have an initial value of 27. That is, we're starting from 27 feet. And then we're going to lose a third of that after every bounce. That is, we'll lose a third or keep 2/3 of it. So our value of b is 2/3, while the percent of decay is 1/3. And now all we've got to do is plug in the appropriate value of x. What will the height of the ball be on the 4th bounce? Well, x is the number of bounces. So let x be 4. And this one we might be able to handle without the graphing calculator. 2 to the 4th power is 16. 3 to the 4th power is 81. So what we've really got here is 27 times 16 over 81, which appears to be 16/3, or 5 1/3, 5.3 repeating. And of course, if you don't believe me, you can always check it out with the graphing calculator. 2/3 raised to the x power here. And let's go ahead and go straight over to the table. And there it is, where x is equal to 4, y is equal to 16/3. Now we know the initial value is 27. So let's have a look at the function, say between when x is negative 2.5 and when x is 10. And then y minimum, we know we're always going to be above 0, so that's fine. Y maximum is going to be at least 27, so let's do 35 and see how that looks in the graph. So this is the shape that our exponential decay functions take. They're always decreasing as you move from left to right. So let's do one more, because these ones on page 776 don't really take much effort at all. And neither do the problems on page 786. You just got to understand what you're being asked to do. So in number 18, that's an exponential decay. It says the population of a town is 18,000 and decreasing at a rate of 2% per year for 6 years. So let's zero in on this thing right here. So my rate of decay is 1 minus my percentage of decay. So if it's a 2% decrease each year, that's 1 minus 2%, which is 1 minus 0.02 for 0.98. And now you're right back to the type of problem you were doing on page 776. You've just got to go calculate the rate of decay, or the rate of growth as the case might be. Your b value isn't being handed to you. You have to do just a tiny bit of work to find it on your own. And then switching back to growth for, say, problem number 30 about the antique car. Our a value is given to us at 32,000. But we have to do just a bit of work to get the the B value, the rate of growth. If the value grows by 7% each year, then it's going to be 7% above that flat line that happens when B is 1. So that's just 1 plus 7%. And of course, you remember that that's the same as 1 plus decimal 0.07. So our value of B, 1.07. And then this problem asks about 5 years. And you can go straight to the calculator to get that answer. So there you go. I hope you guys who are watching this video found that useful. And know that I will be mining these word problems for a possible quiz this week.